Okay, this is a wonderful, very simple theorem. I like it because it shows you the power of a theorem, meaning that theorems show you the constraints that nature, I would say, gives to you. The statement is very easy. Ni minus epsilon plus phi equals 2. The number, if you take the number of, you have a plane graph, a connected plane graph. And if you count the number of vertices minus the number of edges plus the number of faces, then you get 2. Absolutely. And I like this. And okay, I have a course in mathematics, even if it is for research people. But if somebody went to teaching to young boys and girls, I think this is a very interesting theorem, meaning, please see my viewpoint. I was, when I was at the end of the high school, I was actually conquered by graph theory. So I was thinking to go to physics, but then it happened that I got in my hands a book on graphs, and I discovered exactly this part as a thing which was wonderful to me for one reason. Euclidean geometry is absolutely beautiful. Of course, you have wonderful theorems, okay? You get out of a few axioms an incredible world of properties that you deduce in a logical way, and so I admired the logical structure of Euclidean geometry. But there was something inside me which was a little bit refusing it. And it was that it is too perfect, in the sense, if you have a perfect circle, then you have that the angle at the center is twice the angle at the circumference. And if you have an exactly isosceles triangle, meaning that two sides are exactly of the same length, then you can say that the two angles are also equal. But if you don't have that perfect thing, then everything falls down. Okay, geometry, Euclidean geometry, is for something so perfect that whatever you draw is just an approximation of it. Do you agree with me? I mean, have you ever drawn a really perfect circle? It's almost impossible. Whereas what you do in graph theory is perfect. You don't need it to be straight, or you just want to do. Oh, what I say is this: if you have assume that you have to teach a class of people of 10 to 14 years, okay, pick up a sheet of paper, okay, and so you pick up a sheet of paper. All right, then your instructions are that each of the children, you must have at least 2 children for that to be interesting. Each of the children must first of all put vertices here, okay, call it vertices or whatever you want, and then draw lines around, bigger, let's do it bigger. Okay. Okay, and so, and again, like this, and whatever, in the most free way, with only one thing that you can actually, that it makes what we can call a connected graph, so that you can go from each piece to each other piece. And then just take all the crossings, color them green, okay, and color blue all these lines, okay. And you, child, you think you have been free, okay, because it was not the perfection of a circle. No, you were free. Can I do it curved? Yeah, sure, do it curved. Can I do it as a snake? Do it as a snake, no problem. You think you are free, but you are not, because if you count the number of green dots, the number of blue lines, and the number of white faces, then number of green minus number of blue plus number of white is not what you want, is 2. Here, sorry, it will be 1, okay, because you missed the exterior face, okay? So, I think this shows the power of a theorem even more than the power of a theorem in Euclidean geometry, because the implicit assumption in Euclidean geometry is that everything is perfect. Okay, that straight lines are so absolutely straight that circles are actually, all points are exactly the same distance from a point called the center, and so on and so forth. And here you seem to have freedom, but there is a theorem which takes a little bit of freedom out of you. Okay, and this theorem is, this theorem is Euler's theorem. Euler's formula, which is this. And let's prove it. It's very easy to prove, but I wouldn't prove it to children. Anyway, for children, it could show them that there is some magic in mathematics, which are, and magic is theorems. Okay, let's do it. By induction on the number of faces. So, inductive premise. If the face is only 1, what does that mean? It means that you only have cut edges. If you have only one face, then each edge of your connected graph is a cut edge. What are the graphs in which the connected graphs in which each edge is a cut edge? They are trees. So if you just have one face, your graph is a tree. And then we already know that the number of vertices is 1 more than the number of edges, okay? And so actually you have just one face, okay? So let's do it. For inductive premise. Phi equals 1 implies that G is a tree, and then what you have is that ni of G minus 1 equals epsilon of G. Okay, so if you do ni of G, phi of G, ni of G minus epsilon of G plus phi of G, then you get what? You get ni of G minus ni of G minus 1 plus 1, which is ni of g minus ni of g plus 1, which is 2. Okay? So the inductive premise is done. Okay? Now assume that phi is greater than 1. So your graph is not a tree anymore. Okay? If you have at least 2 faces, this means that there is at least one edge which is not a cut edge. Okay? So which separates 2 different faces. Okay? All right. Then what do? You take that edge away. Okay? It is not a cut edge. And so its deletion does not disconnect the graph. Okay? And what happens is that 2 different faces, the 2 faces that edge separates, merge into one single face. An example. Ooh, have I started the? Oh yeah, the recording. Okay. If my graph is like this. Okay, I will not take this one, okay? But since I have at least 2 faces, it means that there is at least one edge which is not a cut edge. Let's take this one, for instance, okay? Here I have face F1, face F2, and face F3. Okay, I'll take this edge away, and then I get only one region out of F1 and F2, okay? And so what happens is what is written here. What is written here is that you take now the this new graph, the graph that you obtain G minus E, the one which you obtain by taking E away. But this has one face less. So you apply now the inductive hypothesis, okay, which says, okay, for this graph, this relation holds inductive hypothesis, okay? And so surely mu of G minus E minus epsilon of G minus E plus phi of G minus E must be equal to 2 because of the inductive hypothesis. Yes, but what do we know about the relation between ni of G and G minus E? They are equal. Did we delete any vertex? No. So these are equals. What about epsilon of G? Epsilon of G is one more than epsilon of G minus E because the difference is exactly that edge which is present in G and not in G minus E. And what about the number of faces? It is phi of G minus E equal phi of G minus 1. And so here we have that this becomes, let me write it. Ni of G minus E. What is this? Minus epsilon of G minus E plus phi of G minus E equals 2. And this is the inductive hypothesis. But this is equal to ni of G. And this is epsilon of G minus 1. Okay? And this is phi of g minus 1 equals 2. And so this is ni of g minus epsilon of g plus 1. Plus phi of g minus 1 equals to 2, but this goes away with this, and what you get is actually what we wanted. Ni of g minus epsilon of g plus phi of g equals 2. Okay? All right. So, for instance, all planar embeddings of a given connected planar graph have the same number of faces. We have seen that they can be non-isomorphic, okay? No problem, but they must have the same number of faces. Why? Because they must have the same number of vertices, okay, the same number of edges, and then what happens is that when you do ni minus epsilon plus phi, it must be equal to 2, and so you get that this phi of g is equal to epsilon g minus ni of g plus 2, and phi of h is epsilon of h minus ni of h plus 2, but epsilon of g is equal to epsilon of h, and ni of g is equal to ni of h. And so you get that phi of g must be equal to phi of h. The numbers are the same, okay? And we also can have some necessary conditions for planarity. We'll also have a very beautiful one, which is a complete characterization. But here we see something which can be of use, for instance, for K5 and K33. So half of the characterization. Well, something which is fairly natural, again, if I have a graph with quite a lot of edges and a graph with the same number of vertices, but a fewer edges, if you had to bet which one is more likely to be planar, I would bet on the one with fewer edges, okay? I'm not saying it is planar because it has, but if I have to bet, I bet for the one with less edges, because the more edges you put, the easier it is that you cannot actually draw them without intersections. Just to be brute engineers and not mathematicians, okay? But mathematicians have a nice and simple proof for something in that way, which is if G is a simple planar graph with at least 3 vertices, then the number of edges is less than or equal to 3 times the number of vertices minus 6. A strange inequality if you want, but which you can directly deduce from what we have before. Let's see. We do it for connected graphs. Let G be a simple connected graph with at least 3 vertices. Then what you have is that since you do not have multiple edges, each face is bounded by at least 3 edges. Are you with me? Okay, we do not have bigons. We have at least triangles or quadrangles or so on and so forth as faces. And so the degree of each face is greater than or equal to 3. But we know, and so out of this, if you sum all the degrees for, so you have, let me write it like this. I have this nasty thing. Oh, okay. Okay, so I have degree of F1 is greater than or equal to 3. Degree of F2 is greater than or equal to 3. Degree of F5 is greater than or equal to 3. So if you sum all these and sum all these, you get what? Here you get the sum of all degrees of Fi for I from 1 to 5. And here you have what? You have summed phi times 3. So 3 times phi. Okay, so actually this is what you get here. Okay, but the sum of all the degrees of the faces we have seen before is twice the number of edges. So twice the number of edges is greater than or equal to 3 times phi, which also means that phi is less than or equal to 2 epsilon divided by 3. Okay, so you get 2 epsilon divided by 3 is greater than or equal to phi. Okay, so if you do ni minus epsilon plus phi, which is equal to 2, as we know by Euler's theorem, if instead of phi we put ni minus epsilon, instead of phi we put 2 epsilon divided by 3, we get here greater than or equal to, okay? And so now we have what? We have ni, and here we have 2 epsilon minus 3 epsilon divided by 3, okay? So minus epsilon divided by 3 is greater than or equal to 2. Am I correct? Okay. Okay. And so out of this we get what? We can take epsilon on one side. Epsilon divided by 3 is less than or equal to ni minus 2, okay, and multiply by 3, and so get epsilon less than or equal to 3 times ni minus 6, which is what we had to prove, okay? Also, if you see a graph in which at each vertex there are quite a lot of edges and one in which some vertices have few edges incident to it, what would you bet? I would bet for the planarity of the one which has some vertices with few edges incident. And this is actually this corollary, which says, again, a necessary condition. If G is a simple planar graph, then small delta is less than or equal to 5. Okay? If you have just one vertex, it is immediate because, of course, if you have a simple planar graph with just one vertex, it must have no edges, and so small delta is 0. If you have two vertices, then small delta is 1, and so no problem. If you have at least 3 vertices, then what do you have? If you sum all the degrees, each of the degree of the vertices is greater than or equal to small delta. And so again, by something very similar to what we have done, small delta times ni is less than or equal to the sum of all degrees, which we know to be twice epsilon, okay? And since twice epsilon is then, because of the corollary before, less than or equal to 6 ni minus 12, it's 3 ni minus 6 multiplied by 2, okay? Then we have small delta times ni less than 6 ni minus 12, and so delta times ni less than or equal to 6 ni minus 12. So if I divide by ni, I get small delta less than or equal to 6 minus 12 divided by ni. Okay? Which means that since 12 divided by ni is anyway a non-null quantity, okay, and small delta is anyway an integer, then this means that it is strictly less than 6, and this means less than or equal to 5. Okay, it is an integer which is strictly less than 6, and this means less than or equal to 5. And so, what are necessary conditions good for if we have a characterization which I'm promising? But they are very good, once more, for the counterpositive, meaning if you have a graph in which you see that all vertices have at least degree 6, you can swear without any other checking that your graph is not planar, or that you have that the number of edges is more than 3 times the number of vertices minus 6. You don't have to check any other thing. You can say that this graph is not planar. Okay? So also only necessary conditions are useful. Let's see now that K5 is non-planar. Okay. What's the number of vertices of K5? 5. What's the number of edges of K5? It's 5 times 5 minus 1, 4, so 20 divided by 2, so it's 10, okay? But then 10, which is the number of edges, has to be less than or equal to 3 times the number of vertices, so minus 6, okay? And this is 15 minus 6, which is 9. So 10 should be less than or equal to 9, which is not true. And so K5 cannot be planar, okay? Just a little bit less trivial is the non-planarity of K33. Okay, again, suppose that it is planar and get a planar embedding, but mind K33 is bipartite, okay, and simple. So no face with 2, with degree 2, no face with just 2 edges around it, but also no face with 3 edges around it, because it is bipartite, and so no odd cycles are possible. And so at least 4, degree 4, okay? And so every face has degree at least 4. And so again, if I sum all the degrees, I get 4 times plus 4 plus 4, 5 times, not 5, 5 times, okay? But then 4 times 5, which is less than or equal to the sum of all degrees, but the sum of all degrees of the faces we know to be equal to 2 epsilon. And what's the number of edges in K33? Okay, for each vertex you have 3 edges going to the other side. Okay, so 3 plus 3 plus 3, it's 9 edges. So twice epsilon is 18. And then we would get that the number of faces, that 4 times the number of faces, is less than or equal to 18, which means that phi itself, the number of faces, is less than or equal to 4. Okay, let's put this into Euler's formula, which says that ni minus epsilon plus phi equals 2. Okay, ni is 6. It's K33, 3 vertices and 3 vertices. Epsilon, we know it's 9. And now phi is less than or equal to 4. But then this gives us 6 minus 9 plus 4, which is 1. And so we would get that 2 is less than or equal to 1, which is false. And so again, we get that our assumption of planarity was false, and K33 is not planar. Okay, so you see, out of Euler's relation, Euler's formula, we get it. But we have much more than this out of these 2 graphs, which is Kuratowski's theorem. Which is a complete characterization of planar graphs. And it's just this. A graph is planar if and only if it contains no subdivision of K5 or of K33. A subdivision, I recall it is substituting an edge with a path, okay? So putting some vertices of degree 2 inside edges, okay? So here you have a complete characterization of planar graphs, which is striking because these 2 graphs are not just 2 non-planar graphs, but they are the prototype, the necessary presence in a non-planar graph. Not themselves, there's some subdivision of them as a subgraph, okay. But they must be there. Either one or the other must be there inside your graph for it not to be drawable on the plane without spurious intersections. Okay? So it is a very strong thing. And so you can understand that there was quite a big hope of solving the 4-color problem that I already mentioned to you. Is any political map colorable with at most 4 colors? Okay. The 5 colorability was known since long, as you can see, okay, 1890, okay, and you can find here a proof if you want, all right. At the moment of writing this book, this was the best known result, that surely 5 colors always suffice. You have already seen the K4 graph, which is planar, okay, and which is not colorable with the 3 colors, but 4 are necessary, and so 4 are necessary, 5 are enough, are sufficient. Is 4 necessary and sufficient? And it was a long-standing problem. and as you can see, it's just in the footnote that they had hastily to put that while they were printing the book, the theorem was actually proved. As I told you, with 1,200 hours of computing of a Cray computer, the most powerful computer in the world at that time. Now, probably it's some minutes of a good PC, still is something that no human can check. Okay? All right. And the last chapter that was in my program, I'll delete it out of the program today or tomorrow. So no directed graphs, unfortunately. I preferred to go slowly and to do things with details and repeat if somebody wanted to repeat. So no directed graphs. I think it is an interesting reading if you want, but it's out of the program now. And since I don't have time for a whole chapter, okay, something in there is understandable. What you do is putting a direction on each edge, okay, and then you call them arcs instead of edge. What changes is, for instance, the incidence and adjacency matrices, okay, according to this. And there are interesting theorems. And they can also represent more of the models that we can think of in terms of something which is representable with the points and lines connecting them. For instance, one way is in the network of streets of a town, okay? You have one ways, and so it is important to say that you can just go from here to there and have an order between the two vertices, okay? Or also moves in a game, okay? Take, for instance, all possible configurations, legitimate configurations on a chessboard of the play of the game of chess, okay? And you can connect one configuration to another if you do a legitimate, if you go from one to the other with a legitimate move, okay? And so you cannot come back with, I don't know the name, the simplest, the soldiers, okay, you cannot come back, all right, with, no, I don't remember the name in English, okay? Or with the bishop, you cannot go vertical or horizontal, okay? And not bishop for that, or you cannot move of just one place with the knight, okay? All right, but if you have a configuration, make a move and get another configuration, then you can have a directed arc from one to the other vertex, okay? And so it is important to have a direction in that. And it is important, I just want now to mention to you something, but I don't know how, no, let me close this. And I would like to recover something out of my Okay, let me give you a glimpse. From now on, everything which I say is out of the program. Okay? No, nothing to do with the exam. Okay. You are too young to know the search engines that came before, were there before Google. We had quite a lot, okay? Lycos, Alta Vista, Yahoo, some more, okay? And they were good enough, okay? But they were easy to cheat in the sense that the important thing was not to find the pages containing your search word, okay? You put horse, okay, it was not difficult for them to find all the pages with horse in it. The difficult thing is always to rank them. What to put as first, second, third, how to do that, okay? And all of them more or less used a very simple idea. Look how many times that word appears inside the page, and that will be the rank, okay? So if you have a page in which horse, the word horse, appears 3 times, it will be higher in the ranking as one in which that appears twice or once, okay? And so how can you cheat? You cheat, for instance, by invisible tags. Something which is seen by the search engine, but not seen by anybody else. So you put there 100 times horse, because you want people looking for something concerning horses to find you before your competitor, okay? And so you put it 100 times. Invisible to everybody, but visible to the search engine. And your competitor sees that you are above him, okay, and he puts it 200 times, and so on and so forth. And so it was blowing up of stupid things like this, okay? And so just by working on your page, you could modify the ranking, okay? Then Google came, and all the competitors were completely thrown out of the game. Why? Because the ranking of Google depends not on the single page, but on all the network, so to say. In this sense, this is why I just mentioned directed graphs, even if they are not in the program, okay? But it's easy to understand what it means. Now take this, take that you have a vertex for each web page, and you have an arc, meaning a directed edge, from one page to another page, if in the first page you have a link leading to the other page, okay? So in this very simple graph, directed graph, you have that page 1 contains a link to page 2 and to page 3, okay? That page 7 has a link to page 1 and to page 5, which has also a link to page 7, and so on and so forth, okay? Now, you have also probabilities, okay? You have probabilities of going from one page to another. Surely Google has some very smart ways of weighing probability of going from one page to another. Maybe a big central link in very big letters will be considered with more probability than a small one at the end of the page, okay? But just for making things simpler, assume that each link has the same probability of being hit, okay? And now think of making what is called a random walk. Okay, and so you go to a page and randomly click links. Okay, without reading. If I go to Chinese pages, I find, oh, this is a link. I click it. Oh, this is a link. I click it. Okay. All right. Question. Are there pages which are more likely to be reached by this random walk? One could think, no, they are all the same. Not at all. Not at all. There is some with more probability than others. And this is by an old theorem which you have in the exactly in the directed graph in the last parts, in the last chapters of the book. And this is interesting because in our book, that theorem is recalled for one thing, for ranking the players in a tournament. If you take a tennis tournament in which every player plays against all other players, and in which you do not have a draw, either you win or you lose, okay, you might have some problems. You can look at this. It is in the book. The problem of having a tournament and you have to rank the players. If you have some players with who have defeated the same number of competitors, how can you rank them? And so you one level over. There is everything is already in our book, okay, referred to ranking the players in a tournament. These two students, Larry Page and Sergey Brin, were so smart to see that this could be taken to the web, and that could rank that same theorem, Perron-Frobenius theorem, something of 1911 or something like this, okay, could give them a ranking. Why? Because you have this. You already know that if you want the think of our normal adjacency matrices, okay? You already know that if you take A to the fifth, it gives you the walks of length fifth from one vertex to another, okay? Now, more or less, if you do the same products of this matrix, which is no more the adjacency matrix, it is a probability matrix of going from one vertex to another in just one step. If you do H to the second, you have the probability of going from one vertex to another vertex in 2 steps, H to the third in 3 steps, and so on and so forth, okay? And then you have that Perron-Frobenius theorem tells you that if you do that, your sequence of infinite sequence of H to the nth actually converges to some, to a sequence, but you don't need to do that because you can immediately find that such a type of matrix has necessarily an eigenvalue 1. Okay, and if you take an eigenvector corresponding to eigenvalue 1, a normalized one, so that if you make the sum of the squares of the entries, you get 1. Okay, eigenvectors are defined up to proportionality factors. Okay, if you have an eigenvector, twice that eigenvector is still an eigenvector of the same eigenvalue. So if you take a normalized one, okay, this eigenvector is what corresponds to taking infinitely many, so to say, powers of this of the of the matrix by itself. So, okay, take this. This is what? It is means you enter in page 1 at instant 0. Here you have the probability of being after 1 click in page 2, page 3. Of course, you are not. Don't have a loop. You are not linking yourself, and so you are not after 1 click. You are not anymore in page 1. You are in page 2 or in page either in page 2 or in page 3 with 1/2 probability. What if you do 2 clicks? It means multiplying by h to the square, okay? And then you have these probabilities. 1/2 of being in page 4, 1/4 of being in page 2, and 1/4 of being in page 5, and so on and so forth. But the interesting thing is that at some moment you stabilize. Okay, for this very simple graph, you stabilize after 60 iterations. But it always stabilizes. When maybe after 1,000,000 multiplications, should you multiply that matrix by itself 1,000,000 times, it is the biggest matrix in the world, okay? Already 10 years ago, when I read a paper about this, it was 1.8 billion rows and columns, okay? The matrix which Google is dealing with. Now it will be much, much more than this. And so you cannot multiply it by itself. But there is this interesting thing. You don't need, because exactly the same numbers here, you find as the normalized eigenvector corresponding to eigenvalue 1, Perron-Frobenius theorem. And so you just know that you have eigenvector 1, eigenvalue 1, you find the eigenvector, and this gives you the rank. This is directly taken from matrix H, but it is what you would get after 60 iterations, so 60 clicks, okay? And if you look, it's exactly the same. And what does it say to us? It says that the biggest probability of being in one of these pages is in page 8, okay? After that is in page 6. After that is in page 7, and so on and so forth. Okay, and so this gives you a ranking of the pages that you have found. And you, of course, you restrict to the pages containing horse and see what happens not just to your page, but your ranking depends on all the network, so to say. Let's say a fairly big neighborhood of your page in this directed graph. Okay, and this makes, of course, much, much more difficult to cheat. It is always possible to cheat, okay, always. But it makes it difficult because you cannot act just upon your page, as was before. You must act upon quite a number of pages in order to make your emerge out of the network because of this trick. And this trick is present in this very book, but refer to quite another thing. And so what is genius? It is a genius, Perron and Frobenius, who saw this thing in the matrix graph. Okay? It is also rather ingenious to think of applying it to the ranking in a tennis tournament, and it is a genius meaning billions of dollars, of US dollars, for these two young students who understood that they could apply it to the web. Okay? This is one of the things I wanted to tell you. And since we are here, I want to tell you something which is not concerning graphs, but is still mathematical methods indeed. And it is the idea of configuration spaces. Okay, you should have studied in your undergraduate studies, normally at the first year, n-dimensional spaces, and you might have wondered, why should I study dimension n when my space is of dimension 3? Come on, let's do dimension 4 if I take time as a fourth coordinate. Why? Because you might have that things are determined by a certain number of parameters. Okay, and let me show some easy situations like this. For instance, okay, you might have this simple thing, colors, okay? Our perception of colors depends on the fact that we have 3 types plus 1, which is not active now because there is too much light. Okay, they are called the rods, and when there is much light, they are out of not out of order, but they are not on duty. In this moment, we have three types of cones active. One which has a peak of answer at 424 nanometers, another one at 530, another one at 560, okay? And the response of these 3 types of receptors in our retina is what makes our sensation of color. You might have thought that color is a frequency. It's not. Not our way of seeing colors. Our way of seeing colors depends strictly on the fact that we have these three types of receptors. And so it's what is very normally used in this screen, in this screen, because it's done by RGB, in the sense that each pixel is actually 3 pixels together, one blue, one green, and one red, okay? And what you see as the color of 1 pixel is exactly given by a triple of numbers between 0 and 255, okay? And so, if you take the colors of the possible colors of pixels in a screen, in a computer screen, the true space which would represent that space of colors is this cube, okay? This cube in which you have that each point represents a color and is given by these three coordinates, which are the tone of green, of red, of green, and of blue, okay? And think of what happens where, we mammalians, I don't want to offend anybody, no, okay. There are Islamic friends here, I don't want to go into delicate things about Darwin, okay, so let's skip it. But something which is definitely true is that birds have a different distribution of receptors. They have 4 types of receptors, apart from the fact that they have also one in what is for us ultraviolet, okay? And so they have a different perception. Not only can they see ultraviolet, which we do not see, but they have a different perception of colors because their perception of colors is actually with one more dimension. Okay, if our perception of colors is three-dimensional, because it is determined by the response of three types of cones, theirs is four-dimensional. We are, in a sense, colorblind with respect to birds. And actually, what happens to our colorblind? Do you want to make a colorblind person angry? You don't want because you are a good girl. But if somebody is nasty, okay, find a colorblind friend. It's very easy because 8% of the male population is colorblind. But meaning colorblind is a bad word because it's not true. They see colors. So if you want to make a colorblind very angry, ask him generally, because generally he's a male. Oh, so you don't see colors, and he will get very angry because he sees colors, but his color space is less dimensional than the normal seeing people, okay? And in the same way, we are colorblind with respect to birds, in the sense that their space of colors is actually one dimensional more. If you take a section at fixed intensity of light, so you get, for us, you get, if you cut here at a certain total intensity of light, you cut with the plane, okay? You cut with the plane and you get, most times, you get a triangle, like this, okay? If you do the same thing for a bird, you take fixed intensity, you get a tetrahedron of possible colors, okay? And so you have that, you have here some points which are not points in a true geometrical space. They are points which represent something else. A color in our vision, a color in the color space of of a computer screen, or the colors for the vision system of a bird. Okay. But you can also have other situations. Take a road in which you have a starting point and other points, okay? I think of bicycle runners along this road, for instance. One is called A, the other one is called B. And so each of them has what is called a curvilinear coordinate. So the distance, simply the distance along that road from the starting point, okay? And so, of course, each of these can be represented, of these positions, can be represented in a line. But if you want to represent the situation of both together, you can represent it as a point in a totally false plane, okay? The plane in which you have the curvilinear abscissa or coordinate of A as x, and the curvilinear abscissa or coordinate of B as y, okay? So this point means the position of both together, okay? And what's the aim of doing something like this? You can, for instance, see if you put two constraints on these configurations. For instance, that B must be 1 unit farther than A. This is a straight line, okay? Or that the distance of point A and B from 0 should be no more than 1. Then you have this square, okay? Are there configurations of A and B on that road which respect both constraints? You just have to intersect this red line with this blue square, and you find this segment. This segment means all the possible configurations of A and B along that road which respect both these conditions, okay? And you can have something like strange, like if you do your good linear algebra, you know that in a four-dimensional space, you might have two planes which intersect just in one point. How can that be conceivable? How can you conceive two planes, one plane in four-dimensional space, and how can they have one point in common? Okay, here it is. This is, you have four runners along that road, A, B, C, and D, and here is a plane, which means two constraints. We have four dimensions, two constraints, then we have something 4 minus 2, two-dimensional. This is a plane, two constraints on A and B, that the barycenter of A and B is at position -3, barycenter of C and D is at position 1, and this is another plane which says that actually C is 5 units farther than A and D is 1 unit farther than A, okay? If you put them all together, you find actually one single solution, which is this configuration, no problem, okay? And you can have other things like this. In the last 3 minutes, something complicated, but in our space, our very space, but which is complicated. The very good trick is that this is something difficult to deal with if you put forces on it, for instance, okay? So you have a complicated object in a simple space, ours. The trick of configuration spaces is to transform this into the simplest possible object, which is one single point, but where does complication go? To the complication of the space. Let me give you this example. No, let me give you this example. I prefer this. You have one piano on a platform which can be turned around, but the platform itself is on a sort of rail, okay? And the rail is in a corridor. And you have all positions of this piano, keyboard, okay, which are determined by the angle with respect to the rail, and this means a circle, and the position along the rail, which means a segment. And so together you are on a cylinder, or on a piece of cylinder. Each point in the cylinder means a position of your keyboard, okay? Because it means a position with respect to the rail, an angle, so a position on the circle, and the position along the rail, meaning a position on the segment. So altogether, a position in this cylinder. Then you might have these problems. You must go from here to here, so from this position to this position, and you have a very wide corridor. No problem, you do as you want. While you go from here to here, you turn around the keyboard and you are there. Now assume that the corridor is tight, okay? And so, but you can do this curve since you start with a keyboard like this, okay? And not all the positions are allowed. You cannot put the keyboard perpendicular to the rail here, okay? So these red points are the ones which are not possible, not possible positions for your keyboard, okay? But you must go from here to here, meaning from this position to this position. No problem, you go up to the end, and then you rotate when you are out of the corridor, you rotate the keyboard. Wonderful. What if the corridor is the same, but you start with this position? Okay, a child of 6 probably would already know how to do, even if it is counterintuitive. Go out, turn, and go back. But maybe a child of 3 or 4 wouldn't be able to do this. But even a child of 3 or 4 could find the solution if you give him or her the configuration space of the problem. And just saying you are here, you must go to A, just by going through blue points. And he or she would very well know that he or she should go like this or the other way around, which means actually get out, rotate, and go back. Okay, configuration spaces absorb the difficulty of the problem, putting this difficulty inside the space. The object becomes very simple, a point. It is the space which absorbs all the difficulties of the problem. This is the end of my module. I'm already in touch with Professor Giuliani, and I've given her the dates of my exam, and we are already in contact, and okay, I hope it will be interesting also that this was interesting for you, and also the part of analysis will be. So I've been very happy with you in the classroom, and with you all outside there in the world, my friends in the world, the class on which the sun never sets, okay? I'm very happy, study quite a lot. I'll give within a couple of days the outcome of the midterm. Next possibilities of recovering the midterm are in my webpage. The first one is on January the 8th. Write to me with your Univo registration number if you want to enlist, but you find all the instructions on my webpage. Ciao, ciao to everybody.
Thank you, Professor. Ciao.
Ciao.